Hi, my name is Narina and we are from Group 4. So what is distillation process? Distillation is a widely used method for separating mixtures based on differences in the conditions required to change the phase of components of the mixture. To separate the mixtures of liquid, the liquids can be heated to force components which have different boiling point into gas phase. First, we have simple distillation, which is commonly used in industrial and laboratory researches, and we have fractional distillation, which is commonly used for petroleum refining since the liquids have close boiling points to each other. And we have steam distillation, which is commonly used to achieve distillation at lower temperature than normal boiling point. And we have vacuum distillation, which is commonly used for substances that have incommonly high temperature when boiling or decompose when boiling under atmospheric pressure.
Now, moving on to the next slide, I'm going to present the question given. It says demonstrate the design process to recover 98 weight % toluene from 1000 kg per second of mixture containing 20 weight % of benzene, 30 weight % of toluene and the remaining xylene using distillation columns in series. Upon seeing this question, there are two main points that need to be highlighted. Firstly is distillation column in series, and secondly is 98 weight % of toluene recovered. Now the concept, we can say that the distillation columns are positioned in series. Secondly, 98 weight % of toluene in any one of the stream, and also 98 weight % total recovery of toluene. This means that based on the feed stream that consists of benzene, toluene and xylene, a total of 90 weight % of toluene from the feed stream will be at the end product.
Hi, I'm Tan Zesen and I'm going to explain about the assumptions that we made in our design. So the assumptions can be divided into two parts, the one given in the question and also the one we made while designing the process stream. So the first assumption given in the question is that the mass flow rate of the feed stream will be 1000 kg per second, including 20 weight % of benzene, 30 weight % of toluene and also 50 weight % of xylene. The second assumption stated is that 98 weight % of toluene need to be recovered in the product. We have designed the process involving two columns. In column 1, we assume 98% of xylene will be recovered at the bottom product, but no toluene is collected here. In column 2, we assign the recovered assumption, which is the 98% of toluene at the bottom product, but none at the top product of this column. We also assume that there will not be any xylene yield at the bottom product of this column 2. Actually, in real industrial process, it is hard to obtain 100% purity out of any stream, as there are many experimental errors or maybe incomplete reactions and undesirable side reactions that might cause in reducing the process yield of the product in the stream.
So next is parameter assumption. So there are two columns in our design process. So for column 1, the temperature set is 145 degrees Celsius and the pressure is 101.3 kPa. For column 2, the temperature set for the bottom product is 130 degrees Celsius and for the top product is 145 degrees Celsius and the pressure set is 101.3 kPa. Next, for the justification, the temperature is varied to control the composition of the product stream. Based on our stream design, the temperature set for the column is based on the boiling point of benzene, toluene and xylene. Lastly, other parameters such as saturation pressure, relative volatility, dew point temperature, bubble point temperature, liquidity of liquid, and viscosity of liquid need to be taken into account. In real-life situation, there will be other components that will help to separate compound from the mixture, such as condenser and reboiler. So here is the boiling point of benzene, toluene and xylene. So now for the justification part. First, the pressure is set constant because we assume it is a steady state distillation. However, in a real-life situation, there will be a pressure gradient across the column. The pressure gradient occurs as the liquid coming down impedes the flow of vapor up the column and imposes a pressure below the flow.
To solve this kind of a problem, we will look into the overall boundary first. In the overall boundary, we will have 5 number of the unknown variable, which is M3, N4, N5, Q and R. And the second step is we need to find the number of the independent equation. So we will have overall balance, mass input equal to mass output, benzene balance, toluene balance, and another two is the additional equation. So the third step is we need to find the number of freedom, which is the number of the unknown variable 5 minus the number of independent equation 5. So we will have 0. So that means this kind of the problem can be solved. And then we will take 1000 kg per second as our basis. So to solve this problem, by using the additional equation number 2, we can get the amount of N5, which is 3000 kg per second. And then by using the toluene balance, we can get the amount of N3, which is 3000 kg per second. As we already get the amount of N5 and N3, we can find the amount of N4 by using the overall balance, which is 400 kg per second. As we already get all the amount of the mass flow rate in all the stream, we can find the amount of Q by using the balance equation, which is Q equal to 0.485. And then as we already get the amount of Q, we can find the amount of R by using the additional equation number 1, which is 0.485 plus R equal to 1, and R we will get 0.515. So based on the calculation that we made above, we already know that 400 kg per second for N4, 300 kg per second for N5, 300 kg per second for N3, and for the overhead product from the column 2, we will have 0.485 kg benzene per kilogram and 0.515 kg xylene per kilogram. And the last step is by using the xylene balance, we will do the checking process, which is the mass xylene input equal to mass xylene output, and we will get 500 equal to 500, which is exactly same. That means that calculation that we already made above are correct. And then we will look into the column 113. So we will have 4 unknown variables, which is N2, X, Y, and Z. And we will also 4 independent equation, which is the overall equation. We will have the mass input equal to mass output, and that's means that 1000 equal to N3 plus N2. And then we will have the benzene balance, and we will have the toluene balance, and the last one is we will have the additional balance. So the most important part in the sorting equation is to find the degree of freedom, which is the number of the unknown variable minus with the number of independent equation. Because the number of unknown variable we have 4, and number of independent equation we have 4 too. So it means the degree of freedom equal to 0. Then this equation can be solved. Then we will take 1000 kg per second as our basis for the stream, like the stream. To solve this problem, first we will use the overall equation to find the amount of N2, because the amount of N3 we already know from the previous calculation in the overall boundary. So the N2 equal to 700 kg per second. By using the benzene balance, we can find the X value, which is 0.29. By using the toluene balance, we can find the amount of Y, which is 0.42. Because we already know the X and Y value, we can find the Z value by using the additional equation, which is Z equal to 0.29, which is exactly same as the X value. In the last diagram here, we can see that the N2 equal to 700 kg per second, while the overhead product here, we have 0.29 kg benzene per kilogram, 0.42 kg toluene per kilogram, and 0.29 kg xylene per kilogram. And the last step is the checking step by using the xylene balance. So that's means 0.5 times 1000 equal to 0.29 times 700 plus 0.98 times 300. So we will get 500 equal to 497, which means that the value is nearly same. That means that the calculation that we made here are correct.
So this is our final design for our distillation cylinder.